Okay, now I am going to start this class. Okay.
Yes, sir.
So I think you have done this. Have you calculated the bending moment and sigma st? In the last class, I have told you to calculate this bending moment and sigma st value. So let me start from this problem. So bending moment, we can write that. So bending moment equals 0.5 and the sigma CBC value is 7 multiplied by KD, and our K value is 0.31. This is the K value, and B value is 300. 1 minus 0.31 by 3 multiplied by 500. Okay. Now you can get the bending moment value, that is say 73.01 kilonewton meter. Okay. Now you have to find out sigma st. You have to find out sigma st. Okay. So you can apply C is equal to T, or you can go through the stress diagram. In this stress diagram, this value is 7, and this value is, you have to find out sigma st by m, and this is 0.31 multiplied by 500, that means KT, and effective depth is 500. So 7 by 0.31 multiplied by 500 equals sigma st by 280 by 3 multiplied by 7, that means 3 sigma CBC, into D minus KT, that means 500 minus 0.31 into 500. Okay. Now you can calculate sigma st, that is 202.55 Newton per millimeter square. Okay, so this is the answer. Now we have complete the section analysis part, and please keep in mind that our goal is to design the structure, not to analyze the structure. Okay, so this is the design of a particular section is more important than the analysis, because ultimately you have to design in real life, you have to design the structure. So suppose you have a bending moment value, suppose x kilonewton meter. Now the question is that you have to design the structure based on this bending moment. Okay, now what are those parameters? Please you have to remember that one parameter is grade of concrete, another parameter is grade of steel, and next width of the beam or width of the section, and depth of the section, and there is another parameter. You have to keep in mind that this is our, suppose this is our section, and in this section you need to determine the width of the beam, the depth of the beam, and the number of reinforcement. Okay, you have to calculate now. But how you can calculate all those parameters? All those parameters are unknown. Okay, so in this case we don't know what is B, we don't know, we have to calculate or we have to find out. We don't know what is effective depth. Okay, now we have to calculate AST also, this is also unknown, and we have to calculate, we don't know the sigma C value, that means grade of concrete, stress of concrete, and we don't know the stress of steel value. All those parameters we don't know, we have to find out. We know only the bending moment only, and we have to design this section. Okay, now you have some formula. One formula is that you can apply bending moment equals C into lever arm, and another formula is T multiplied by lever arm. Okay, and you can create another formula from bending stress diagram. That means you can use the bending stress diagram, and in this stress diagram you can see that one parameter is sigma C, another parameter is sigma ST or sigma S, another parameter is neutral axis depth, neutral axis depth, or another parameter is effective depth. Okay, effective depth. Now Using this similar triangle, you can find one of all those parameter: sigma c, sigma st, sigma cbc, neutral axis depth, or ed. If you know the neutral axis depth and sigma st and effective depth, you can calculate this sigma c value. Or if you know the sigma c value, neutral axis depth, and effective depth, you can calculate the sigma st value. Okay, like that. If you know sigma c, sigma st, and effective depth, you can calculate the neutral axis depth. Okay, so you don't have any other formula. Okay, so how you can design this particular section? You have to measure, you have to calculate all those parameters, and all those parameters are unknown. So first of all, what you can do, you just you can fix the width of the beam. Okay, width of the beam you can fix. How you can fix that? By keeping in mind the architectural point of view. That means suppose we have a frame structure. Okay, and in this frame structure we have some column, some beam. Okay, like that. Suppose this is the cross section, this is the beam section, bottom of the column, and this is the this is the column, and this is the topmost beam. Okay, and on this beam, suppose one slab is resting, okay, over the beam. Now you have to fix this width. Okay, now suppose the width of the column, or width of the, suppose there is a section, hollow section will be created, because two column at both sides. Okay, now this is the tie beam, this is the topmost beam. Okay, now this hollow section will be filled up by a brick. Okay, brick wall. So the thickness of brick wall is, say, 250 is the generally thickness of the brick wall. Now you can fix the width of the beam, say 250, so that the width of the beam and width of the wall will be matched. Okay, or what you can do, you can increase the this width of the beam, say 300. Okay, so like that you can fix the width of the beam. Now you please keep in mind, we have one formula, that is bending moment is equal to half sigma cbc j k b d square. We have this formula. Okay, and we have another formula, that is bending moment equals sigma st ast jd. Sigma st is t and jd is lever arm, and half sigma cbc jkbd square is total formula c multiplied by lever arm. Now you have to design this beam based on the bending moment. That means we know the bending moment value. Okay, now based on the architectural point of view, you can fix the b. So now b is fixed. Okay, now b is fixed. You see, in this equation we have 1, 2, 3, 4, 5 unknown. we have 5 unknown and 1 known, that is bending moment. So it is impossible to solve this equation with 5 unknown, because if we have one equation, suppose 2x plus 3 is equal to 9, say this is one equation, so we can say that this we can solve, we can calculate the value of x. Now you have this equation 2x plus 5y minus 2 equals to 8. So you can't solve this equation because this is only one equation and you have two unknown, x and y. So to solve this equation, you need two equations. Okay, suppose 3x minus 2y plus 7 equals to 3. So if you have two equations, you can solve two unknown x. You can get the value x and y. Okay, so from this is only one equation and you have to solve it. That means at the end of this creation of this equation, you must have only one unknown. Okay, so now we know bending moment and you know the width of the beam B. Now what should be the depth of the beam? Depth of the beam, that means if this is effective depth, this small d denotes by effective depth. Okay, so depth of the beam, suppose we have one reinforcement here, and to keep the those reinforcement in particular position, we are placing at the top two reinforcement. Okay, so these two reinforcement are working only to keep this bottommost reinforcement in particular position, and we make some ring over here. Okay, so it can be strong enough. Now what is the effective depth? Effective depth means from the topmost fiber of the beam to the center of the tension reinforcement is the effective depth. Okay, this is the effective depth. Now when you are going to cast a particular beam, you have to create a formwork. Okay, now suppose this is the formwork you have to create. This is the formwork. That means the depth of the formwork, at the inner side, depth of the formwork should be equal to the overall depth of the beam. Please keep in mind, depth of the formwork should be equal to the overall depth of the beam in the inner side. Okay, now if I say that you just create a beam whose overall depth is say 573 millimeter. Okay, is it possible to create this type of beam? It is very difficult. Okay, so that's why we generally assume that the overall depth of the beam should be in a round figure, say 500 millimeter. Okay, say 500 millimeter or 550 millimeter, you can say. So generally, or 600 millimeter or 400 millimeter. Okay, so generally we keep this overall depth in round figure. Okay, now overall depth is this. This is the overall depth. So effective depth equals overall depth minus clear cover. This distance is clear cover. Let me draw it again. Suppose this is the stirrup and this is one reinforcement. Okay, now this distance is clear cover, and this distance is dia of stirrup. Okay, so dia of stirrup, and we have to measure the effective depth from the center of the tension reinforcement. Please keep in mind, center of the tension reinforcement. Now you can calculate the effective depth, that is overall depth, capital D. We always use capital D to denote the overall depth. So overall depth minus clear cover minus dia of stirrup minus dia of tension reinforcement by 2. Okay, so this is D. Okay, effective depth. Why I have done this? Because we have to keep in mind that the overall depth should be in round figure. Overall depth should be in round figure, because you can calculate the or you can use the value of the effective depth with some this type of figure. Suppose 593.26. You don't have any problem, because you just using this value to calculate or to design this section. Okay, so you can use this type of value as a effective depth, no issue, but you can't use this type of value for overall depth. Okay, so always keep in mind that you have to assume the overall depth, and next you have to minus clear cover and minus the dia of stirrup and minus the half of the dia of reinforcement, tension reinforcement from the overall depth, and you can get the D value. Okay, now we know the value of B and value of D. Okay, now you just think that what should be the value of K. If I get K, you can calculate J, no issue. Okay, so J value is depends upon the K value, and what should be the K value and what should be the sigma CBC value. Now those two are unknown, K value and J value. Okay, now K value depends upon the type of section. Type of section is under reinforced, balanced, and over reinforced section. Okay, so you can use under reinforced section, you can use balanced section, you can use over reinforced section, no issue. But suppose you in your semester you can directly use the balance section. That means you know the value of sigma CBC. Okay, so now you know the value of sigma CBC. So in this case, now you have only one unknown. Bending moment is known, sigma CBC value is known, B value is known and D value is known. So you have only one unknown, and J is depends upon K. So if I say this is actually 1 minus K by 3, then only K value is unknown. Okay, so you need to calculate the K value, nothing else. Now this is only one part of the design. That means you fixed the dimension of the cross section of the beam, dimension of the cross section of the beam. That means B and D, and you need the reinforcement also. Okay, so how you can get the reinforcement value? From this equation. Okay, in this equation you have the let me write it again. Bending moment equals to sigma st st jd, sigma st st jd. Now from this equation you know the K value. Okay, you solve this equation, you will get the K value. Now from the K value you can get the J value, and D value is already we know that. Okay, now bending moment is known, J is known, D is known. Okay, now what should be the sigma st value and AST value? Sigma st, I have told you that you can assume the section is balanced section. Although it is not actually possible to create a balanced section, you can't create it practically, but you can theoretically you can solve this problem assuming that this is the balanced section. Okay, now if it is balanced section, then sigma st value also known. Say suppose Fe415 is our grade of steel. For this case you know the value of sigma st, say 230. Okay, now bending moment is known, JD is known, sigma st value is known. Now this is only one equation and this is only one unknown, AST, and you can solve this equation and you can get the AST value. So how we can design a particular beam section? Now let me clear it. Bending moment equals half sigma CBC JK BD square, and bending moment equals sigma st AST JD. Okay, now if you assume that this section, our section is a particular balanced section, then suppose it is a balanced section, then to solve this problem, to design this section is very easy, because for this case you know all those things. Sigma CBC value you know, sigma ST value you know. Okay, and K balance value you also know, or you can get from the stress strain diagram directly. Okay, so you can get the stress strain, get the K value from stress strain diagram. Now bending moment is known, BD also known, and K value is known. Now you can, or sigma CBC value is known. Now you can calculate the K value directly, or you can neglect this equation because you know the K balance value. You can directly apply this formula. Okay, only putting the value of D. Okay, so you can calculate the AST value. What should be the AST? Okay, now it will complete the one part of the design, that means based on the bending moment. Please keep in mind we have only two parameters. One is bending moment, another is shear force. We have to design against the bending moment, we have to design against the shear force. So shear force in future I shall show you. the how we can design against the shear force. No issue. Now I think it is clear to you that how we can design the particular section against the bending moment. Okay. Now this B is known, this effective D is known, and effective D is coming from overall depth. Okay, overall depth minus clear cover minus dia of theta. You can neglect dia of theta right now, no issue, or you can assume that. Okay, so dia of theta you have to minus deduct from the overall depth and minus the reinforcement, dia of reinforcement by 2. Now you can get the D value. Okay, and you can calculate the AST from this equation. Now you have only the value of AST, and if you divided this AST by particular area of one reinforcement, you can get the number of reinforcement. Okay, number of reinforcement. Okay, now when you are going to design, first of all you have to know the bending moment value, and second you have to know the or you can assume the width of the beam. Next you can assume the overall depth of the beam. Okay, next you have to select the grade of concrete. Okay, so grade of concrete, next grade of steel, next dia of stirrup, next dia of reinforcement, I should say tension reinforcement, and next clear cover. Okay, so and next you have to assume that this section is balanced section. Okay, now suppose we have a structure, simply supported beam. This is the point load. Suppose there is some point load W. Okay, and this length is L. So the maximum bending moment will be this. This is the maximum bending moment. Suppose this bending moment is suppose 100 kilonewton meter. Suppose this maximum bending moment is 100 kilonewton meter. Okay. Now based on this bending moment, I have to design this beam as a balanced section. Okay. So what I can do, first of all, assume that in this section, this is the width of the beam, say 300 millimeter. And depth is say 500 millimeter, and this is overall depth. Okay, now I have to assume the dia of reinforcement dia of tension reinforcement, say dia of tension reinforcement is say 12 millimeter, and dia of stirrup say 8 millimeter, and clear cover say 20 millimeter. Now you can calculate the effective depth. So effective depth D equals overall depth 500 minus clear cover 20 minus dia of stirrup 8 minus reinforcement dia of tension reinforcement 12 by 2. Okay, now this will be 500 minus 20 minus 8 minus 12 by 2. So 466 millimeter. This is your depth or effective depth. So suppose this is the effective depth. Okay, now from the we are assuming that this is balance section. We are assuming that this is balance section. Okay, now you have to write it, because okay, I am not going to write all those things, because it is very difficult to write with the help of mouse. Okay, so in your semester you have to write that we are assuming that this section is balance section. Now from the stress diagram you know that okay, we have to assume the grade of concrete also. So or it may be given in your question. Okay, suppose grade of concrete is M20 and grade of steel suppose Fe 415. Okay, now this value is 7, this value is 230. You know that this is coming from IS 456 table 21, and this is coming from IS 456 table 22. Okay, now our effective depth is 466. Okay, what should be the K balance value? Now you can use the formula for K balance. This is 280 by 280 plus 3 multiplied by 230, that means sigma st. Okay, and this value is 0.2886. This is your K balance value. Now you just calculate the AST value. So 100 multiplied by 10 to the power 6, because this is in kilonewton meter and I have to change the unit. Okay, so bending moment equals sigma st, that means 230, AST, I have to find out the AST, into JD, and J value is nothing but 1 minus K by 3, 1 minus 0.2886 by 3, and D value is for how much? 466. Yes, 466. So now you have to calculate AST. So AST equals 1032.31 millimeter square. Okay, so this is your AST. Now you have to find out the number of reinforcement. Okay, so we have assumed that the 12 millimeter diameter bar. Now number of reinforcement equals 1032.31 by area of the one reinforcement. Okay, area of the one reinforcement means pi by 4 multiplied by 12 square equals 9.127. Okay, so we can't provide the 9.127 number of reinforcement. Okay, so we have to make it round figure, and please keep in mind we can't reduce the number. Okay, we can't reduce the value, we have to always increase the value. Say the number is 10, not 9. Okay, so for this case, for this balance section which will resist the 100 kilonewton meter moment, the section is 300 B, 500 overall depth, millimeter unit, and there is 10 number of reinforcement. Okay, so ten number of 12 phi bar. Okay, so this is the design for this balance section. Okay, you got my point? If you have any doubt, you please tell me. Okay.
Yes, sir.
So up to this, is it clear to you?
Yes, sir.
So no doubt. ভাস্কর মন্ডল,
হ্যাঁ স্যার,
কোনো ডাউট?
হ্যাঁ স্যার দেখছিলাম, ডাউট সেরকম নেই।
ওকে, অমর্ত্য ভট্টাচার্য,
Yes sir.
any doubt?
No sir.
Okay. Anish Kumar,
Yes, sir.
any doubt?
No, sir.
Manob, hello. Okay, now I think I shall give you one problem as a homework. You have to design a particular section. Okay, I have shown you the how to design the balance section. Okay, now how to design the under reinforced section and how to design the over reinforced section.
স্যার এটা হোমে ট্রাই করব?
না না, আমি বলতে দাও আমাকে। Under reinforced section, please keep in mind, in under reinforced section the steel reaches its permissible stress at first. Okay, so first of all, in the stress diagram you know only the value of stress in steel, no, not for concrete. Okay, and in our over reinforced section the value of stress in concrete you know, and not for steel. Okay, now how we can design as this section as a under reinforced and over reinforced. First of all, I shall give you a homework. So, okay, so let 155 kilonewton meter is the bending moment. Okay, 155 kilonewton meter is the bending moment, and you have to do it. You have to try. Okay, how we can design it as a under reinforced section and over reinforced section. After that, I shall tell you. If you make any mistake, I shall tell you. No issue. Okay. So this is the homework for you. Okay, number one. And okay, today I shall stop here. In the next class I shall show you how to design the doubly reinforced section. And doubly reinforced section means nothing but say, we have in reinforcement in tension side and also in compression side. Okay, so this is called doubly reinforced section. How you can design the doubly reinforced section, what should be the formula, I can start from the next class. Okay, so now I shall stop here. And if you have any doubt, you can tell me now. Ronnie Mahanto,
Yes, sir.
you have any doubt?
No, sir.
Okay. Okay, let me take the attendance. Okay. $29.